So we're going to take a look at thermochemistry. Again, remember, you're going to use this strategy of collaborating with your thought partners to do think aloud paired problem solving. But for now, we're going to take a look at the quiz question for today. So remember, you've got a two-part quiz. The first part is individual. The second part is collaborative. So for this quiz question, you were looking at 2 liters of a gas collected at 25 degrees Celsius and 745 millimeters mercury. And then you want to know what is its volume at 0 degrees Celsius and 760 millimeters mercury. So if we take a look at this, we have V1, we have T1, and we have P1, and then we have T2, and we have P2, and what they're asking for is V2. So that's super helpful for us because then we can go through and we can identify our P1, V1, N1, and T1. And notice, right, we've got a little bit of a dilemma. We're being asked to solve for volume, but we don't know moles. That's actually not a dilemma because it allows us to do 2 things. The first thing is we're going to assume that the number of moles does not change, and so that allows us to cancel the number of moles. The second thing that we're going to do is rearrange to solve for V2. So remember, this is using our changing gas laws equation. So we're going to isolate algebraically our V2. And so in order to do that, we have to multiply both sides by T2. That cancels T2 on the right and puts T2 in the numerator on the left. Then we're going to divide both sides by P2. That allows us to cancel P2, and that means we're left with V2. So V2 is equal to P1, V1, T2 divided by T1, P2. So if we do that, then we can substitute and solve. So we're going to take everything that we were given in the equation and substitute in. So we have 0.98 atmospheres. Remember, we have to convert our millimeters mercury to atmospheres. And we multiply that by 2 liters and by 273.15 Kelvin. Then we divide by 298.15 Kelvin. 1 atmosphere, that gives us 1.79 liters. But in this case, we need 1 sig fig. So that means it's 2 liters that we solve for. Super excited to share with you our scientist spotlight. So this is Francois Bar-Sinouisi. She's a virologist at the Pasteur Institute, and she's responsible for isolating the viral particles that are responsible for HIV or the human immunodeficiency, also known as AIDS. And she was awarded the Nobel Prize for her efforts with her colleagues from the Pasteur Institute. But what I really want to focus on is that she viewed science as something that we did or engaged in for the benefit of humanity. And so because of her advocacy, she created the International AIDS Conference as well as the International AIDS Society that provides resources to individuals suffering from HIV or AIDS. Now, this is really important because in a lot of ways it was the advocacy work early on in the discovery of the disease that made a difference for individual patients. So when we think about HIV today, we think of it as a disease that's considered chronic. So because of the medications that we can use to treat it, it's important that we recognize that those didn't necessarily exist right away. They were developed because of scientists like Francois. So the human immunodeficiency virus, or the acquired immunodeficiency syndrome, AIDS, is something that we now know today because of work by virologists like Francois. And this is relevant today because there are individuals currently doing research on COVID-19 or the coronavirus. And so it's because of virologists like Francois that hopefully we will have treatment as well as testing for the coronavirus soon. So if we think about science practices, that's important because we want to ask questions and define problems. That's really, say, for example, what Francois is doing. They're trying to understand why a certain disease results, and they analyze and interpret data to make sense of patterns in the disease, And then they construct an explanation, say, for example, that HIV was caused by a virus and not a bacteria. And then they engage in argument from evidence. So being able to isolate and determine what virus was responsible for causing this disease was really the work that Francois and her partners did. So if you think about our learning outcomes for chapter 5, we're going to use the first law of thermodynamics to set up calculations that involve the transfer of energy, heat, work. And so we're going to use some equations to make sense of that. So we're going to talk about our system versus our surroundings. And then we're going to think about the direction of energy flow. And then we're going to use the correct sign, so positives and negatives, to describe the direction of energy flow. We're going to convert between joules, kilojoules, and calories, and then we're going to be able to define total internal energy. So one of the things we can start to do now is really think about starting and maintaining a list of equations. So we're going to make sure that we can label each equation for what it is we use it for, what variables are found within that equation, and then what units we use. And we want to make sure that we engage our visual memory to make connections between these abstract equations and real experiences. So as much as possible, you want to connect things that are known in your knowledge and memory framework to these new and abstract concepts. So we think of energy as the capacity to do work. Work is force acting over a distance. And when we think about internal energy, we think about the sum of both kinetic and potential energy. So kinetic is the energy of motion, it's thermal, whereas potential is the energy of position or composition. And we typically think of that in a chemical sense. And notably, either capital E or capital U of a system is what we use to represent the sum of internal energy. And we know that energy is neither created nor destroyed. So this is the total energy of our universe is constant. This is what we refer to as the first law of thermodynamics, or the law of conservation of energy. But we do know that energy is transferred and transformed. So if we think about then how we transfer energy, we're going to transfer that energy either as heat or as work. And so our total internal energy is going to be equal to the sum of heat and work. And if we think about our changing internal energy, a change is always going to be final minus initial. So if we're thinking about a change in energy, it's our final energy minus our initial energy. So I want you to think about that from a practical standpoint. Let's tie this to something that you know. Which molecules move more, the hot water molecules or the cold water molecules? So if we write a claim, evidence, reasoning statement, then one of the things that we can say is, oh, look, we recognize that the hot water molecules move more than the cold water molecules. And how do we know that? Well, you can think about examples like boiling water or steam. And, right, we can also think about the fact that when we look at boiling water or we look at steam that has the physical properties, say, for example, if you had it in the pot, that looks very different than what cold water in a pot looks like. And our reasoning for that is that molecules in hot water move faster, they collide more frequently, and that these collisions then increase the pressure. So this is an example of a very practical, common experience that most people have. So you can think of boiling water for pasta, or if you're steaming vegetables. And then the reason for that is that the molecules in the hot water move faster, and those collisions result in pressure. So our heat and thermal equilibrium is such that thermal energy flows as heat from objects with higher temperature to objects with lower temperature until they reach the same thermal equilibrium. That's useful because if we think about molecules at two different temperatures, these molecules are going to come in contact with each other. They're going to continue to move until they attain the same thermal equilibrium. That direction of energy transfer then is something that happens to the system, which is the thing that we're interested in, relative to the surroundings. And our surroundings are the rest of the universe. So if we think about the change in energy of a system, it's going to be the result of a change in energy of the surroundings. So for example, if the change in energy of our system is less than 0 or negative, that means our system is losing energy to the surroundings. If our system's energy is greater than 0, then it's gaining energy from its surroundings. You might be wondering at this point, how do we determine what are systems and what are surroundings? So we can really determine this by specifying whatever it is that we're interested in studying. So for example, if we were studying two nested styrofoam cups with a cardboard cover and a thermometer, we could define just the chemicals that are in the solution as our system, and then everything else as the surroundings. So the solvent in the cup, the container, the air above the liquid, the thermometer, which means the only thing that we're studying as our system are the chemical reactants themselves. Now, the reason this matters is because if we're looking at the direction of energy transfer, we have a system losing energy, or we have a situation where our system is gaining energy. So, if we're looking at heat, our system loses thermal energy to the surroundings. This is what we refer to as an exothermic reaction. Whereas if we think about a system gaining thermal energy from the surroundings, this is what we refer to as an endothermic reaction. When we think about work, it's our system doing work on the surroundings or the surroundings doing work on the system. And what's beautiful about this is we can actually use signs to help convey this information. So for example, if I have positive heat and positive work, then I'm going to have a positive change in energy. Whereas if I have positive heat and negative work, it's going to depend on the size of the heat and the work, whether or not my change in energy will be positive or negative. So for example, positive for heat means the system is gaining heat. Negative means the system is releasing heat. If I think about that in terms of work, positive means I'm doing work on the system. Negative means work done by the system. So let's think about a really practical example, and we'll identify the signs. So if, I have fuel that's stored, the energy that left the system as heat, our Q is less than 0. The work that's done by the system on the surroundings, our work is less than 0. So the energy of the system decreased. The overall energy of the system is less than 0. So this is something that's very commonly seen if, say, for example, you were studying an explosion. You have incredible potential energy stored as chemical reaction that then release that energy. And this would be an example of the changing signs on Q, W, and the energy of the system. If we think about measuring energy units, the unit joule, is reflective of our kinetic energy, or 1/2 mv squared. And this has the units of kilograms times meters squared per second squared. So 1 joule is 1 kilogram meter squared per second squared. So you can think about this if you want to connect it to E equals mc squared. We can also measure energy using calories. So the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius is 1 calorie, or 4.184 joules to be exact. It's more common for us to use kilojoules or kilocalories. And so let's look at an example then of energy transfer as heat to or from an object. So Q is what represents heat in joules. The change in temperature is T final minus T initial. And then C is the heat required, or the capacity, to raise the temperature of the object by 1 degree Celsius. Now that's going to be really useful because we can also modify this equation to say if we're transferring the heat to an amount of an object, we can say Q is equal to mcs delta T. So in this case, again, Q is heat, M is mass, delta T is the temperature change, and then CS is the heat capacity that's required to raise the temperature of 1 gram of the substance by 1 degree Celsius. So you're going to notice that we have two equations here. One is energy transferred as heat to or from an object, and the other is heat transfer to an amount of an object. We'll start to look at some examples of this next class, but a good way to start to conceptualize it is that metals have low heat capacities. They're really good conductors of heat, whereas water has a high heat capacity. It has a tendency to stabilize atmospheric temperatures, or for example, it's used to stabilize nuclear reactor cores because it has such a high heat capacity. As a quick recap, remember about S cubed after class. Don't forget about your discussions. We'll get some great practice in there today. And during the last 5 minutes of class or today, make sure you take time to organize your goals, think about your thinking, and reflect on your learning. Next class, we'll follow up with thermochemistry and making a little more sense of our heat transfer. Thanks again. Have a great day.